In this video, we're going to go over an important result from communication theory. It's called the Shannon-Hartley channel capacity theorem. And hopefully as we go through this, you'll understand exactly the ramifications of this theorem. I mentioned in a previous video when I introduced information theory about how important it was in terms of telling us what is possible with a communication system. Okay, so it's kind of a difficult topic, so I'm going to break this up into steps. I wanted to give you a roadmap of where we're heading with this first video in the series. First of all, we're going to start with a statement of the theorem. And then we're going to have a discussion about signal levels. And if you add signal levels, you add bits per message that you send through the channel. Okay, for example, if you had 2 signal levels, then you would have 1 bit per transmission. If you had 4 signal levels, you'd be sending 2 bits of information per transmission. And as you increase the number of levels, especially in powers of 2, you add numbers of bits per transmission. So I wanted to talk about that, but with signal levels comes a power constraint. And what that implies is that you can't just make the signal levels spaced as far apart as you would like. There's a restriction on how far apart signal levels can be to meet a power constraint. And once you have a constraint on how far apart levels can be, then you are looking at the effect of noise. Because if you add noise, you won't be able to tell these signal levels apart. Okay, so we're going to talk about that in a video and how that all plays together in forming the channel capacity theorem. From there, we're going to look at another video. All right, so think of this is step 1. Okay, we're covering the statement of the theorem and we're mapping out a roadmap. And then in step 2, we're going to give some basics of signal levels, power constraints, how noise would affect that. Okay, and then we're going to talk about the effect of bandwidth. Bandwidth gives you a constraint on how fast we can send pulses through a system. And because we can only, a pulse, think of a pulse as a message that we're sending through the system. If the message has multiple signal levels, we can represent more bits per pulse. And so that gives us a path into communication rates. Okay, so that's going to be part of another video. And then from there, once we get to that point, we can come up with a sort of a justification, if you will, or maybe plausibility would be a better word. But the actual proof of the channel capacity result is pretty difficult and beyond the scope of this course. So we're going to do a justification of the result, because in many ways this justification is more useful for a communications engineer than to actually know the full details of the proof. Okay, so if you understand sort of the basics of why it might work, that gives you a lot of intuition about communication theory in general. Okay, so we'll have another video that covers these 2 topics. And then finally, there's some implications of the channel capacity result. People start looking at something called the power limited case. So for power limited case, they're talking about effectively you have plenty of bandwidth, maybe it's even infinite or at least large compared to the signal to noise ratio. So we'll look at the power limited case and also the case where you have a constraint on bandwidth. and you have plenty of power. All right, so we'll trade off large SNR case, so that'll be a case. And then there's something called the Shannon limit. So we'll go over that case as well. So those are the 3 videos that I plan to have in this series. It's actually 4 videos when you include this introduction video. And so we'll move on from there. Okay, so the statement of the channel capacity theorem goes like this. Let's say we have a system that we're trying to communicate information from. All right, this could be speech or music or video or text or whatever. Okay, you have a certain rate that you're trying to send this information. Okay, I like to represent this as little r times h, where r can be considered the number of messages that we send per second. And h is the entropy of the source. We talked about source coding before, so the implication here is that we figured out a way to efficiently represent the information. Okay, so all this part is the idea of source coding. And a lot of times that gets lost in the discussion of the channel capacity theorem. We're assuming the source coding step has already happened, and we're already most efficiently representing the source with some kind of data compression scheme. Okay. In many cases, that's not true. We haven't even tried to do source compression. We're just looking at how can we send data at a rate of R through a communication system. The channel capacity result still applies. You just have an inefficient R value. Okay, so we can talk more about that if you have questions about it. So the idea here is that there's a channel capacity, and C is given by the bandwidth of the channel. You take log base 2, 1 plus the signal to noise ratio. Okay, where S is the signal power and P is the noise power. This is matching the notation in your textbook. Okay, I'm going to add a little subscript B here, and oh, by the way, B is bandwidth in hertz. Okay, I'm going to add a subscript B because it turns out noise power is a function of bandwidth. Okay, so a lot of times people will, when they're considering this result, they'll use the white noise case. Okay, so here's the spectral density of white noise. It's just a constant. But if we are only transmitting over a certain bandwidth, okay, let's say we modulate our signal and we're only using this bandwidth, okay, then the noise power is just the area under the curve, area within this bandwidth. All right, so as you expand bandwidth, what happens to the noise power? The noise power goes up. Okay, so you can't consider those independently of one another because they're related. Okay, so there's some other results that take care of the case where the noise is not white, it's not flat like this, but when people are talking about the channel capacity theorem, generally they're expecting additive white Gaussian noise as being part of that model. Okay, so the channel capacity result says that if R, that information rate that we're trying to send through the channel, is less than C, all right, we can communicate all this information with arbitrarily small probability of error. Okay, so arbitrarily small is an engineer's way of saying essentially 0. It's hard to get down to exactly 0, but you give me an error rate I can come up with some coding scheme that will achieve that error rate. Okay? So the converse to this theorem is also true, that if you have R greater than C, then there is no way, no way to communicate without error. Okay, and generally without significant error where it's not really even possible to communicate. Okay, so that's the idea. We're going to learn this trade-off between bandwidth and signal noise ratio and how fast you can communicate over a channel.